So we will start in a minute.
Yeah, okay.
Yeah, so Professor Ajay Kumar sir, can you start?
Yeah. Okay. It's a matter of great pleasure to introduce Professor Narayanan, or in short, we call him Naru, and he's a well-known harmonic analyst. His main area of research and interest is harmonic analysis on semisimple groups. And he'll be talking about the Plancherel Theorem on SL2R. So, as we all know that for type 1 groups, there is a Plancherel theorem. And but in this case, probably it is an explicit expression, and it is hard job to find an explicit expression for the Plancherel measure. I hope all of you will enjoy his lecture on this Harish-Chandra proof of Plancherel theorem on SL2R. Naru, if you'd like to start.
Yes, yeah, okay. Thank you, Ajay.
Mm.
So first of all, let me thank the organizers for asking me to give this series of lectures. In particular to Devendra. I know he has put in a lot of effort to make this program happen for a year, in fact. And well, I'm sorry I wasn't able to go to Pune to give these lectures because of various commitments here. So in these lectures, I will explain the representation theory of SL2R, which is the simplest of the semisimple groups. And in the last lecture, I'll try to give the proof of the Plancherel theorem. So one has to classify the irreducible unitary representations, which actually appear in the Plancherel formula, and then prove the Plancherel theorem, which means there is a measure which gives an L2 isometry result, right? So the proof of the Plancherel theorem is due to Harish-Chandra, which of course he more or less executed for general semisimple groups with some conditions. Okay, but some of that is contained in the posthumous volume which Varadarajan and Ganguly brought out some time back. But the SL2R proof is much old. All right, so with all that, let me start. So where is the sharing thing? Yeah, okay. Okay. All right. So, okay, I hope you can see the screen now. Can one of you please confirm?
Yeah, that's perfect,
okay.
right?
Okay, yeah. Yeah, all right. So I'll start, and if there are questions, please feel free to stop me. I gave these lectures at HRI in October, and this will be essentially a repetition of that. Okay, so if you had already attended that, then there may not be anything really new except the last lecture where I'll try to give the proof of Plancherel theorem. Okay, so let us start. So G is going to be SL2R. So what is SL2R? So this is all 2 by 2 matrices with determinant 1, right? So AD minus BC equal to 1. Okay. So all the ABCD are real numbers. Okay. now, whenever you have a matrix group, there is a associated Lie algebra. Well, if you have a Lie group, there is a Lie algebra, but we will not be talking too much about Lie groups. Here, many things are explicit. So the Lie algebra, so this will be the Lie algebra. The algebra, it will be denoted by G or sometimes small SL2R. This is going to be all 2 by 2 matrices whose trace is 0. Well, the definition in the linear or for matrix groups is you look at all e to the tx, also all 2 by 2 matrices such that e to the tx is in G for every t in R. Okay, so that is your Lie algebra, and it is easy to prove that this consists of all those matrices whose trace is 0. So trace of x is 0. So all trace 0 matrices. Okay, where, well, so the exponential is the usual exponential. So e to the x is summation x to the n by n factorial, right? So n equal to 0 to infinity. Remember that x is a matrix, but it's easy to prove that these things converge and so on. Okay, and from general theory, one knows that the exponential. So sometimes I will write x also. So let me write it here as well, exponential of x. So x is a map from the Lie algebra G to the Lie group G, right? So from the Lie algebra SL2R to the group SL2R. And this one knows that is a local analytic diffeomorphism. Okay, so analytic diffeom. Okay, so it's a, well, it's a nice map. And G, the Lie algebra G is like a vector space, right? So three-dimensional real vector space. And so the exponential can be used to give coordinates for the group G, which makes it into a real analytic manifold. So there are certain subgroups one should consider. So subgroups of SL2R, which are important from our point of view. Okay, so one is so let's go up a little bit here. Okay, so K is SO2. So this is a maximal compact subgroup of SL2R. So we'll use the notation K sub theta for the matrix cos theta minus sin theta, cos theta, where theta belongs to real line or 0 to pi. So that's just a circle group, right? And k theta will denote this. So depending on the book, so you look at some people write it as cos theta by 2, sin theta by 2, and so on. Okay, so one has to be careful about what representation one is using. So it's known that K is maximal compact subgroup of G. So G is going to be always SL2R in these lectures. And it's also known that any other maximal compact is conjugate to K, right? So you can conjugate by an element in G to K. Now the other two subgroups. So one is A, that is abelian A, and we will denote these matrices by A sub t. So e to the t by 2, 0, 0, e to the minus t by 2. Okay, with t in R. So again, depending on the book, you look at, some people write e to the t and so on. So all these things, all these minor changes make it a bit difficult when you read some other books. Okay, so but one has to be careful about it. Okay, so this is abelian. The n is a nilpotent group. So, and this is 1, psi 0, 1. Okay, psi n r. Okay, so you can see how these groups are, and it's easy to see that they are all appropriately isomorphic. So the n is actually real line, essentially the real line, right? And so on. Well, why did I write down all this? So we have the Iwasawa decomposition. Iwasawa decomposition. So G is actually Ka. So K, remember, is the maximal compact subgroup, which is the circle group. A and N are, you can see it on the screen. So this is a general result. Okay, so any semisimple Lie group with appropriate conditions. So for example, connected semisimple Lie groups with finite center, you will have a maximal compact K. And you have a decomposition called the Iwasawa decomposition. So most of the things I say are actually true in general. Okay. And not just this decomposition, there is a, so if you look at the map from K cross A cross N to G, which is, so let's say K comma A comma small n, going to the product. So product is given to be G, right? So this is a onto map, and it's actually a diffeomorphism. It's a diffeomorphism. Okay, so it's 1, 1 onto C infinity, and its inverse is also C. So this is called the Iwasawa decomposition. One has other decomposition called the Cartan decomposition and the polar decompositions. So let's write down Cartan decomposition. Cartan decomposition. Let P be the set of positive definite matrices in G. Okay, then each x in G can be written uniquely as x equal to Kp, where K belongs to K and P belongs to P. Okay, that's a linear algebra exercise. And well, one also has that the map K comma P going to Kp is again analytic diffeomorphism. Now the P is a positive definite matrix, so you can again diagonalize it. Okay, so which gives us what is known as the polar decomposition. Okay, so corollary. Okay, polar decomposition. Okay, so I can write G as KAK. Right? If I take anything from P, I can diagonalize it using orthogonal matrices, so that K will, so I can write it as K1, A, K2, right? A will be diagonal, right? So that's what this is. So that is the polar decomposition. But this is not unique, right? This is not unique, one should remember that, but one can make it unique by restricting the, AA corresponds to the eigenvalues and so on, right? The diagonal entries. So you can make sure that eigenvalues in a certain order so that it is unique. Okay, so you can let A plus. So that is the positive part in A. A, remember, is e to the t by 2 and e to the minus t by 2, the diagonal matrix. So I can make sure that A is of certain form, e to the t by 2, 0, 0, e to the minus t by 2. But I take t greater than 0, so that so that defines a certain order for the eigenvalues, right? So then G is equal to K A plus bar K, and if I take element in G x not equal to 1, then this decomposition is unique. Okay, so then this decomposition is unique. Okay, so those are decompositions. So I have we started with the group SL2R. We have these three groups K, A, and N. K is the maximal compact, which is the circle group. A is just diagonal matrices, and N is the nilpotent part. Okay. Now we will use all these subgroups. So if you have a question, please unmute yourself and ask, because I won't be able to see any of you. Okay, because
Sir, in
I
the
get a
first
message saying somebody raised a hand. Yeah.
in the first decomposition, I mean, is there ordering matters or is
Which is the first decomposition?
the Iwasawa decomposition?
Iwasawa. No. So okay. So G. So there are all kind of decompositions. You can take G equal to Kan. If you take the inverse, you will get an AK, and you also have Kna and all that.
Okay.
So all sorts of decompositions are possible. Okay. Well, depending on your taste, you stick to one decomposition. So I like Kan. Many people like NaK because when you quotient with K on the right, that K goes away and so on. But I will stick to K. Okay, so this is just some preliminaries on G. Our aim is to look at representation. So I should tell you what are representations or what kind of representations we are looking at, right? So let us see representations. So representation is so from G, I have a homomorphism to let's say bounded operators on some Banach space V. So this is bounded operators on a Banach space V. So we are defining Banach space representation. Okay. So pi is a homomorphism. So pi of G1, G2 equal to pi G1, pi G2. And we also need some continuity assumptions. Okay. So for every V in V, the Banach space, the map G going to pi GV is continuous. Okay, that's an extra thing we will put. So this is a map from the group G to the Banach space V, right? So this immediately implies, because it's continuous, if I take a compact subset of G, so let us say K is already used. So let's take capital X, which is contained in G, and X compact. Then the uniform boundedness principle will tell you that if I take supremum over G in X, norm of pi G, that is fine. Okay, because it's pointwise bounded, right? Because I'm looking at a compact set and I'm looking at G going to pi GV for each V, right? So that's a continuous map. It's bounded on capital X because capital X is compact. And so it is pointwise bounded, so it's uniformly bounded. Okay, so it follows immediately from uniform bounded. Now, if instead of a Banach space, if we have a Hilbert space, if V is a Hilbert space, and pi G is unitary for every G in G, then we say pi is a unitary representation. Yes, then pi is a unitary representation, and we will generally be looking, most of what we do will go through for Banach space representation, but we will be looking at unitary representations more closely. Okay, so those are again definitions, and then we need to know what are irreducible representations. So if W contained in V is a closed subspace, so closeness is important, and pi G of W, remember pi G is an operator on V, right? So for each G, pi G is a bounded operator on V, right? So if pi G W is contained in W for every G, then we say W is invariant. Okay. It's an invariant subspace. And if there are no non-trivial invariant subspace, phi is called a irreducible representation. Okay, so phi is called irreducible if the only invariant subspaces are either 0 or the whole space, right? So there are no non-trivial invariant subspaces. Then we say phi is irreducible. Okay, so our aim is to look at to classify unitary irreducible representations of SL2. Okay, so that is what we will be doing. Okay, so now what happens in representation theory is depending on the structure of the group, there are many things we can do. So if I start with a group G, let's say it's a topological group, then you can, so and let's say you have a representation phi, right, to some Hilbert space, say unitary representation. So unitary operators on a Hilbert space H. You can integrate this representation to get a representation of L1G or CCG. Okay, so L1G is all integrable functions. Remember, G has a Haar measure and so on. CCG is the continuous functions with compact support. Well, how do you integrate? So you look at F in let's say CCG, and then you can define phi of F to be integral over G FG pi G D. Okay, one has to make sense out of this, but that's not very difficult. So what I mean is, if I take a vector V, phi f is an operator acting on V, which is given by Fg times pi GV. So remember that pi G's are uniformly bounded on any compact set, and F comes from CCG, right? So the integral is not on G, right? It is actually on support of F, which is a compact set. Okay, so the norm of this, so if I take the norm inside, it's going to converge absolutely. So there is no problem in defining this for L1 functions here. Now, or in any case, phi is a unitary representation, then the norm is 1. So there is no problem. Okay. Now this works in general for topological groups and so on, because you are not using any other structure. And then one can study these representations using the L1. L1 is an algebra with respect to convolution and so on. But if G is a Lie group, like SL2R, then you have the Lie algebra. Okay, and then you can differentiate. So here you integrated the representation. For the Lie algebra, you differentiate, and you will get a representation of the Lie algebra to some space here. Okay, some set of operators. They actually, in the infinite dimensional case, they happen to be unbounded operators and so on. And so pi dot of an element of the Lie algebra will act only on a dense subspace of H. Okay, so it need not be a bounded operator. So that requires some work. Like so there are analytical issues here. What is pi dot to start with? You have to differentiate. I'll give you the definition. And then pi dot is going to act as an unbounded operator on H. And the set of vectors on which it will act are called smooth vectors or C infinity vectors. Okay, so that is what we will be looking at first. So first we will look at this part, which is EC. So recall that the continuous functions with compact support is an algebra. Algebra meaning there is a product, right, with respect to convolution. Okay, so f star g at x equal to integral over g f of x y inverse g y dy. Okay, and this is also, of course, since both are compactly supported, the convolution is also going to be compactly supported. So it's an algebra. And recall the definition of phi of f, right? So phi of f is equal to integral over g fg pi g dt. right? So that is the integrated representation of CCG. Okay, so so you can prove that. So some of the proofs I will not do here, because some of these are very easy. So check that phi of f star g is phi f times pi g. Okay, so pi f is a bounded operator. Okay, there is no problem because this is a unitary operator, right? So when I take the norm of pi f, that will be less than or equal to modulus of f, and the norm of pi g, that is 1, right? So norm of pi f is the operator norm is less than or equal to L1 norm of f. Okay, so that is a well-defined bounded operator on H. Okay, and so these products are all fine. Okay, so it is a representation of the algebra CCG with respect to convolution, right? The product in CCG goes to the product of the operators, right? Now, it's an easy. So, what is the advantage of doing this? So, it's an easy proposition, which I will not prove, is that if W contained in V is closed, sorry, it's invariant. So invariant always will mean closed. Okay, so we are not going to look at anything which is not closed. So is invariant with respect to G, that is with respect to all pi G, G in G, if and only if W is invariant with respect to CCG. Okay, that is with respect to all pi f, where f is in CC, right? So that is a set of operators, right? So this follows by choosing an approximate identity in CCG. Okay, so this is a straightforward exercise. So this connects invariant subspaces. So invariant subspaces of G with an algebra, right? With the invariant subspaces of the algebra CCG. Now, what we are going to do is we will do a similar thing for the Lie algebra, but as I mentioned earlier, there are certain analytical difficulties which we have to overcome, which is what we will do in the first 2 lectures. Okay. So now let us restrict ourselves to SL2R. Okay, so all this is true in general for any G, but now there are certain things which I will define which is true only for SL2R, even though there is a appropriate analogous expression for other G. Okay, so pi V
is S. So I
yeah.
have a question. Is
Yeah.
SL2R unimodular?
Yes. Yeah, I should have said that. Thank you. Yeah, SL2R is unimodular. Left armature is also right arm. So pi V be a unitary representation of SL2R. Sorry. So remember the groups K, A, and N, but K is more important for us. K is SO2. It is a circle group, right? So circle group, you already know the representations are just given by the characters e to the in theta. So what we do is we restrict the representation pi to K, right? So pi is a representation of the bigger group as L2R, restricted to K. K is compact. So any unitary representation of a compact group decomposes. Okay, so define for each n in Z, define the space V sub n. So V sub n is going to be all those vectors in V which transform according to the nth representation of K, right? So pi of K theta, remember K theta is that matrix cos theta minus sin theta cos theta, acting on the V. So I want it to act like the nth representation, that is e to the in theta, right? So e to the in theta or e to the minus in theta, e to the in theta V. Okay, yeah. So this is a particular subspace of V, right? Of course, it may be 0 for some n. Okay, doesn't matter. But this is the definition which we will use throughout. Now, so easy theorem about these V. And so think of the representation being restricted to K, and we are analyzing it there because we know everything about K and its representations. Okay. So each Vn is closed. Okay. And Vn intersection Vm equal to 0, or equal to 0 if n is not equal to m, because they transform according to different characters, right? So of course they will be the direct sum Vn n in Z. So now I'll take this because I'm on a Hilbert space and so on. I'll take I'll say that these are orthogonal, and the orthogonal direct sum is equal to V, right? So I'm saying Vn is orthogonal to Vm, and the algebraic direct sum n in Z. So that is the algebraic direct sum, which means I take only finitely many, right? Is dense in V, right? That is what this sign perp means, right? This is the usual Hilbert space orthogonal direct sum is V. This is sort of straightforward, but let me give you one line just to convince yourself that this is all fine. So this is like you take a V in V and look at the function V going to theta going to pi k theta V, right? So you can expand this in the Fourier series, and this is precisely what the second one means. Okay. So if you want to write down a proof, you may have to write down few more lines. So define En equal to, so these are going to be operators, e to the minus in theta pi k theta d theta. Okay, so these are operators, right? Pi k theta, remember, is an operator on the Hilbert space V, and I'm multiplying it. It's a unitary operator. I'm multiplying by e to the n theta and integrate. So there is again no problem, and so it's easy to see that. Check that the Ens are projections. Check that En are projections, and if I apply it on the whole Hilbert space V, I'm going to get V. Okay, and from that everything will follow. Okay, so if you have done Fourier series, you have seen this earlier, right? Instead of pi k theta etc., you will have a function there, and these are the Fourier coefficients. And when you sum up those Fourier coefficients, multiply by e to the I k theta, you are going to get your function back, right? All right. So so this is already the first step, right? Given a unitary representation of SL2R, I have a certain decomposition, right, into VNs. I don't know which VNs appear. Okay, some of the VNs may not appear. Some of the VNs may be 0. Some of the VNs have to appear because if I look at this function, this is if V is non-zero, this is a non-trivial function. So some of the Fourier coefficients of that will have to survive, right? So there are VNs and they are non-zero. Okay, so the whole Hilbert space on which the representation acts decomposes into representations of K. Okay, this is all we have done. This is a standard trick because K is compact, and so you know how things are for compact groups. So you are restricting your representation of G, the bigger group, into the smaller group K, and then decomposing it and analyzing. Okay, this is something which you generally do in representation. Okay, any questions at this point? Yeah, so if not, I'll continue. So let me give you the list of, so I'm not going to define these representations right now. In fact, yeah, it's kind of funny that we may not use the explicit expression until the last lecture. So one knows all the unitary irreducible representations of SL2R. Of course, we are going to classify them and realize them on function spaces. Okay, but let me give you the list first. So unitary irreducible representations of SL2R. Okay, so this classification is due to Bargmann. So there are 3 sets or 4 sets depending on how you want to write them. One is the principal series. So right now I will not define them. Well, maybe I'll say a few words. Okay, so what is principal series? So remember the group G, we had G equal to KAN. Okay, so let me define another group M. This is plus or minus identity. Okay, in general, this is the centralizer of A in K. Okay, so here you can compute that to be centralizer of A in K, meaning elements in K which commutes with A. A is just diagonal, right? So you know, if something in K commutes with diagonal, then that also will have to be diagonal, and you will see that it is plus or minus 1. That's a straightforward computation, and it's possible to, so you can define this group P equal to MAN. Okay, well, you need to know that it is a group. I'm just multiplying some matrices. I don't know whether it is a group, right? So it is a group. It's a group. That is also not very difficult to prove because A normalizes N, which is also not difficult to prove because these are 2 by 2 matrices. You can compute them and see that A normalizes N. And from that, it will follow that P equal to MAN is a group. This is called the minimal parabolic. Subgroup. So that I'm not going to define what it is. Now, the principal series is obtained by inducing the representations of characters of MAN to G. Okay. So take a character of MAN. Well, so a character of MAN will look like this. So let us look at the groups again. So I have M to be equal to plus or minus identity. So if I look at representations of M, so I use M hat to say unitary reducible representations of M. And there are only 2 of them. One is the trivial representation, and other is the non-trivial representation, which we will call the sign representation, right? Okay. So you take a character of M and you take a character of A. So A is like the real line, right? So for each lambda, I have a representation of A. Okay. So take a lambda in R. So that gives me, let's say, chi lambda. And representations of N, you take trivial. Well, why are we taking trivial representations on N? MAN, if you look at the commutator subgroup of MAN, you will see that it is N. So any character of MAN has to be trivial on N. Okay. So character of MAN is going to look like, so something from here and something from here, right? Product of that. Okay. So let us say sigma tensor chi lambda tensor trivial. Okay. So sigma belongs to trivial representation or the sign representation. Okay. So that is some representation which depends on lambda and sigma, right? So let us call this I should rho. Okay, so rho lambda sigma. Okay, so that is a representation of MAN. Okay, so again, I'm just multiplying. So you need to know that it is a representation because of A normalizes N and the P MAN is a group and things like that. Okay, so again, some computation needs to be done. But this turns out to be a character of MAN, and then you can look at the induced representation from MAN to G using this particular one. Okay, so that gives me what is known as pi lambda sigma. Okay, so this is your principal series. Okay, so when sigma is trivial, then I will not write sigma. Okay, so when sigma is sign representation, I'll write pi lambda minus. Okay, so let me write that. So phi lambda when sigma is trivial, phi lambda minus when sigma is the sign representation. Okay, so that will be the notation. So there are two sets of unitary irreducible representations. Well, there are certain issues here. So all of these are unitary and irreducible. Unitary irreducible when sigma is trivial. When sigma is sign, it is when lambda in R minus 0, this is unitary and irreducible. Unitary is easy because you are inducing from a unitary representation, you will get a unitary representation. Okay, but at lambda equal to 0, it is not, and phi 0 minus is not irreducible. It splits into two irreducible representations, which are called the mock discrete series. So I have D1 plus and D1 minus. These are called mock discrete series or limit of discrete series. Discrete series. Again, some of this will be defined at a later stage. So that is one set of representations. So that is the principal series. Now we have the discrete series. Discrete series because they appear discretely with counting measure with certain weights. Okay, with certain measures in the Plancherel theorem, and that is dn plus and dn minus. Okay, not negative, not inverse. Dn minus n greater than or equal to 2, right? So n equal to 1 comes here, okay, n greater than or equal to 2, and dn plus is the holomorphic discrete series, and this is the anti-holomorphic one. Essentially, you take the complex conjugate of the holomorphic discrete series. Okay, now there are other representations. So essentially, the first two are the ones which will appear in the Plancherel theorem. There are two more. So two more meaning, well, I already said D1 plus and D1 minus, so that is already included. So there is also complementary series. Complementary series. Well, it's called complementary because it does not appear in the Plancherel theorem, or the Plancherel measure is 0 there. Here in the Plancherel theorem. Okay. And these representations are explicitly realized on function spaces. Okay, so that is something I will write down at some point. Okay, so now what we are going to do is to analyze the representations using the differentiation technique, so that we differentiate representation, come down to the Lie algebra. Okay, so for that we need, so as I mentioned earlier, unlike the finite dimensional representation, so I should have said this earlier, there are no finite dimensional unitary representations of SL2R except the trivial one. Okay, so all are infinite dimensional representations, and we will talk only about infinite dimensional representations. Now, when I take an infinite dimensional representations and I want to differentiate and get a representation of the Lie algebra, this is what you will do in finite dimensional representations, right? If you have seen compact Lie groups and all that, this is something which you have already seen. Now, in the finite dimensional case, when you differentiate, you still get an operator, but that is on the finite dimensional space. So there is no question about boundedness, unboundedness, and all that. But when we are talking about infinite dimensional representations, there are analytical issues. When you differentiate a representation, you are going to get something which is an unbounded operator. Okay, so it will act only on a dense subspace. Okay, so we'll look at that dense subspace first. Okay, so these are called C infinity vectors or smooth vectors. So pi v is a Banach space representation or unitary representation. Unitary representation of SL2R. Okay, then a vector v in capital V is called C infinity, called as C infinity vector or smooth vector, or a smooth vector if x going to pi xv is C infinity, right? So this is a map from the group G to the Banach space or the Hilbert space V, right? X going to pi xv. Pi x is a bounded operator on V and applying on V. So it's a property of the vector V. Okay. So if I can differentiate this as many times as I want, then it's called a C infinity vector. And we will denote V super infinity to be the C infinity. Okay, clearly a subspace. Right, if I have V1 and V2 to be C infinity vectors, then V1 plus V2 is also C infinity, right? Because you are adding two C infinity functions, you will get a C infinity. Now, this is, well, we'll see that this is a dense subspace. First of all, it's not clear that there are C infinity vectors, right? You don't know to start with. We'll show that it is actually dense. And so you have a nice dense subspace on which the Lie algebra is going to act. Okay. So that's called a guarding space. Guarding space. So you take, so how do you construct C infinity vectors? So let's take a function which is C infinity. Okay. And you take any vector V in V, then pi f. So remember pi f is simply the integration, right? You integrate f against the representation. Pi f, that's a bounded operator on your Hilbert space phi. So apply it on V. So claim is that then pi f is a C infinity vector. Okay, so there are lots of C infinity vectors. You take C infinity functions and then apply it on any vector, you are going to end up in V infinity. Well, why is that? So what do you need to show? So to show that x going to pi x acting on pi f v, right? You want to show this is a C infinity vector. So you look at x going to pi x acting on that vector and you want to know if it is C infinity, right? But what is this? Well, this is pi x integrated f of g pi gv, right? Integrated representation. Okay, so pi x will go inside because it's a bounded operator, and pi is a homomorphism, right? So pi x will get f of g is a complex number, so pi x pi g will become pi of xg. Okay, so I will have, so let me write down one more step. So this is fg pi xg v. There is a dg and all that. And then you can remember dg is the Haar measure, so it's left and right invariant. So I can change this x here and put it on f, right? So that would be integral over g f of x inverse g, right? So yeah, should f g changes to x inverse g, right? So it is x inverse g pi of g v. Okay. So now it is the map x going to this integral, and f is C infinity, right? So that makes it a C infinity function. Okay. So any C infinity function, you apply it on a vector on V, you are going to get a C infinity vector. Okay. So now if I take a approximated, so choose Fn in C infinity G, approximate identity, then pi Fn V will converge to V for every V. Okay, that is a trivial exercise. Fn's are approximate identity, meaning they sort of converge to the Dirac measure at identity, right? That is what you mean. And if you write down the integral and take the norm inside, you will see that that happens because of continuity and shrinking support. So that tells me that, so this is for every V in capital V, right? So But these are all C infinity vectors, right? Pi f and v, they are all C infinity vectors. So V infinity, the space of C infinity vectors contained in V is actually dense. So that's a huge space, right? So you take, so this is the first step, right? So you take any unitary representation, and again, this works in general, right? There is no SL2R here. Any unitary representation of G, then the guarding space, which is constructed using C infinity functions, is dense, and the guarding space consists of C infinity vectors. So you have smooth vectors which are dense, and you will see that we can apply the Lie algebra elements on that. Okay, so let us see how. Since I have some more time, I'll just define that. Okay, so for X in the Lie algebra and V in V infinity, define phi dot of X. So phi we'll use for the group G. Okay, and pi dot will be the representation for the Lie algebra G. Okay, so phi dot of X. Of course, we haven't proved anything for the Lie algebra yet. So I'm going to define the Lie algebra action on C infinity vectors. Okay, so V is in V infinity. So we are looking at the smooth vectors, and phi dot of X acting on V is given by, this is the differentiation which I was talking about. You differentiate your representation. Phi of X dx acting on. Okay. So at least for people in functional analysis operator theory, this is something which is quite familiar. Remember, pi is a unitary representation. So T going to pi of X dx is a unitary group, right? So by Stone's theorem, ut is given by e to the something, right? E to the ith, where h is self-adjoint, right? So the ih is your pi dot x. Okay, so that is all is there. So, but it can be an unbounded operator, right? If you have seen Stone's theorem, you know, so you can take an unbounded self-adjoint operator and make a unitary one parameter unitary group out of it, right? So the pi dot x can be a unbounded operator. Okay, but so it acts on C infinity vector. So C infinity vectors will be smaller than the domain of H in the functional analysis parlance. Okay, so check that. If V is in V infinity, then phi GV is also in V infinity, and phi dot x V is also in V infinity. Okay, so for every x in the Lie algebra and for every G in G, right? So both the group and the Lie algebra will leave the C infinity vectors invariant. So we have an action of the Lie algebra on C infinity vectors. Okay, so so I'll stop with this proposition to say that we actually have a representation. Okay, so this proposition will not prove, but it can be proved exactly like the finite dimensional. So phi dot of x bracket y. So remember, x is, we have the Lie algebra, and the x bracket y is xy minus, right? X bracket y is xy minus yx, right? The usual matrix multiplication there. So pi dot of x bracket y is nothing but pi dot of x, pi dot of y minus pi dot of y, pi dot of x. Okay. So because of whatever is written here, we are not going out of the C infinity vectors. Okay. So if I apply it on a C infinity vector, pi dot of x, V is also C infinity, so I can apply another pi dot of y there. Okay. So in other words, this is so pi dot is a Lie algebra representation. Lie algebra representation, which is a purely algebraic concept. Okay, so when we define representations for the group, there is a continuity assumption. Here there is nothing like that. Okay, there is it's a purely algebra concept, right? So you have a Lie algebra, which means a vector space with a bracket operation, and pi dot is linear and respects the bracket operation. Okay, so that is why it is. Okay, now, so because of this, V infinity is a G module, meaning there is a G action, right? The Lie algebra G action, which is given by pi dot. Okay, so maybe I can stop here and start with universal enveloping algebra in the next class.
Yes, any question, please?
Hello, sir.
Yeah.
Um, in the initial one, you had the decomposition as K, A plus closure, K.
Yeah.
So could you explain that closure thing, if possible? Like, what was
I see.
the...
So, okay, 1 second. Let me go there. Yeah. So we have Kn and yeah. So G equal to K, A plus closure K. So A plus closure will bring in. So if you look at A plus, it is T greater than 0. A plus closure will bring in the identity.
So will it be something like we are looking at the positive cone and then...
Yes. So A plus is the positive. Well, I wouldn't say cone. If you go to the Lie algebra, it becomes a positive cone.
Okay.
But at the group level, we don't say it as the cone. But yeah, so that is what it is. And A plus closure is just so in this case, it's rank 1. So it is only missing the identity. Otherwise, you can miss the walls and so on. Yeah.
And when we are talking about the smooth vectors, so as a map from G to B, what would be your definition of smoothness, sir? Like differentiation of the map? So I can go into local chart with respect to G.
Yes. Yeah. So G is a manifold. It's a real analytic manifold, and you can apply that definition. So when I say it is infinity, it is differentiable in the usual sense, right? So infinitely many times differentiable.
Okay. Because sometimes,
but not with respect to the weak. I mean, so okay. So this is something one should say.
Yeah, the vector value.
Yeah, it is vector valued and it is differentiable in the strong sense. So you are looking at the limit of. So if you go to a local chart, you are looking at something from say some open set in Rn to V.
Yes.
And it is differentiable. So you look at f of x plus h minus f of x, etc., and the limit should exist in V.
In V, right.
So V has a norm, right?
Right.
So the limit should exist in that norm in V. We are not composing this map with a linear functional and going to the complex numbers. That is not what we are doing.
Okay.
Yeah.
Okay.
Because it may not give you the same thing, but for analytic functions, that is enough. Weak analyticity, strong analyticity, all of them.
Because sometimes they also replace more general spaces like Fresher spaces instead of looking at Banach spaces.
Yeah. So everywhere there is a topology.
Right.
So C infinity means some limit exists, and that limit has to be in the topology in the space.
Right.
But when you talk about analyticity, you can always take the weak definition. They are equivalent. Yeah.
Equivalent. Okay. Thank you very much. Thank you.
Yeah. Okay. So maybe I can stop sharing.
Yeah, you can stop maybe.
Yeah. Okay. So we meet tomorrow at the same time, or?
Yeah, exactly same time.
Yeah.
Thank you.
Thank you, Ajay sir, for coming to chair this talk also.
Yeah, I think Ajay is muted. So